Hi, welcome to online tutorial videos from Labs. For more information and to download the source code of the video, you can visit us at www.jcbrlabs.org. In this video, we'll talk about how to design and analyze filters in Matlab by using its inbuilt filter design toolbox. So open Matlab. In Matlab, go to the app settings, and then in app settings go to this filter design and analysis. So let's focus on the window only. In this filter design toolbox, there are several options. This particular area shows the filter amplitude or filter response, or the amplitude response of the filter, and this area defines what kind of filters you want to choose or you want to analyze. There is the filter order, and it shows the frequency specifications of the filter, and here we can show like magnitude response specification, like whether we want to display it in terms of dB or or on a linear scale. Here it defines the structure of the filter information, like how many tabs or what is the order of the filter and how many tabs are there, so and so. So we'll try to visualize the different responses of the filter going from low pass to high pass. So let's first select a low pass filter. So here there are several other as well, low pass, like raised cosine, half band, low pass, Nyquist, and so on. So let's take a low pass filter, and then here we can define like what kind of filter we want to choose, like equiripple or Windows filter. So let's say let's put it as it is, and we can here specify the order or the minimum order filter, and let's specify the order of 10, and then units in hertz. Sampling frequency, let's say we have 8000. So depending on the 8000, let's say, because it comes under the category of speech kind of filter, because the speech signal filter specifications are up to 4 kilohertz only, and for that we used to sample our speech at 8 kilohertz. So let's say we have 1000 kilohertz up to only. Alright, now there are two things, pass band and stop band. So if you are familiar with the typical characteristics of the filter response, then you know f pass is the cutoff frequency where the magnitude is up to the limit, and f stop is the cutoff frequency from where the stop band starts, and in between these two, the f pass between f pass and f stop, this is known as the transition period. So we will try to make that transition period as small as possible. So let's say it's 1200 f stop, and let's say design. So the filter is designed, and this shows the response of the magnitude response of the filter of this filter, and order is 10, it's stable, and so on. We can also visualize the phase response of this filter. From this amplitude response, it is clear, like up to 1 kilohertz it is 3 dB bandwidth, and then after that from 1.2 kilohertz around, its stop band starts, because it's equiripple, so FIR response comes out to be this kind. Now let's say its phase response, just click here, will show the phase response of the filter. It is linear, so most of the times these FIR filters are used due to this linearity property of the filter, because the phase of the signal linearly varies with respect to the frequency. And here we can also display the magnitude and phase response simultaneous side by side. This green curve shows the phase response, and this blue curve shows the frequency response. Similarly, we can also put group delay, phase delay, and several other properties can also be seen. Like we can also see the impulse response of the filter as well. So this shows the impulse response of this filter particular, and you can also visualize the step response and we can also visualize the pole zero plot. So in FIR there is only there is no pole, only zeros are there. And then we have filter coefficients, like because it's a 10 order filter, so these filter coefficients are important in order to identify, like or in order to design in some other application. And there's magnitude and response estimate as well. So this shows it. So now let's define high pass or the same low pass filter with IAR filter. And IR has several other types like Butterworth, Chebyshev, and the same order 10 and let's say same specifications of 8000 Hertz and 1000 kilohertz. Let's then click on design filter. This shows that low pass Butterworth filter. The with FIR is its magnitude response is quite good, but there is a problem with the phase response because it doesn't vary linearly with the time. So it shows its response and within and this shows a decay period. We can also increase the order like to 20. This transition period will be more sharp than. So I think it's done. Yeah, that's done. Similarly, we can also visualize like Chebyshev filter with the same specification of 8000 and 1000 passband frequency, and we can also design. So in Chebyshev there are some ripples in the magnitude band, and these are visualized here. We can also visualize it, zoom it a little bit. Yeah. So in Chebyshev, some of these ripples are being observed in magnitude response, but the best part is the roll-off factor is good, and similarly it's the frequency response of the filter. So like this you can visualize several other filters as well, like, and you can see how this filter behaves in those cases. Like it shows the elliptical filter, so up to here, up to the cutoff frequency, it goes like parabolic, but after that its phase response is quite disturbing. And it shows the uh, magnitude response, and this elliptical filter finds very application. It provides a sharp cutoff frequency, so as soon the frequency just after the 1.1 kilohertz is being stopped, but that was not the case with Chebyshev. Oh, and this is achieved at the cost of some phase response. So if we look at the response, again ripples are there, but they are compensated with respect to this response. So let's try to change the order of this electrical filter to 10 and see what changes are there. Yeah, this roll-off for transition period gets increases. So again, based on our application and based on our tolerance limit, we can define what kind of order we can use for the filter. Similarly, it's phase response also that change. So let's say we provide a band pass filter. So in the case of band pass filter, we need to define two frequencies of the pass band, and let's say we have a specific order of this 10 only, and let's change the frequency to 8000, and like first pass band is 1000. And so in this case we are defining like from 1 kilohertz to 2 kilohertz band only we will pass on those frequency, and for other kind of frequency we will stop all those. So let's say design filter, and this shows the response. So only this band will be allowed to pass and all other band will stop. Similarly, we can also have a higher order elliptic filter, and it shows a greater or a steep cutoff uh, for a steep transition period, which is required in many of the speech applications, many of the biomedical applications as well. And similarly, we can have FIR kind of F cutoff. So in FIR, we have several parameters like starting 800, then FPass 1000, then FPass 2 is 2000, and FPass 3 is 2020. So you can change these values as per your need. And yeah, this shows its magnitude response, and then from 1 to 2 it's passing the frequency, and for all other frequencies stopping them. And so for FI we can increase the filter order, and if we increase the filter order, the magnitude response doesn't deteriorate, but we get the quite this stop band attenuation is quite high in that case. So let's say if we have 100 or whatever filter, amplitude is again good, uh, the response of the filter is again good, but and the amplitude response is also good. So FIR, generally in FIR filters we need to have higher order, while in the case of higher filters we prefer lower order. I go to the this phase response. So this was the transition period, or it was the pass band from 1 to 2, and it is quite linear in shape of this FIR filter, and that is why it's find most of the application in, again, in several applications where phase response is also critical information of the signal. So I hope you understand how to use this filter design and analysis toolbox of Matlab. And prior to implementing your filter in hardware or in Matlab, you can verify the response of those filters, and you can either choose, you can visualize how the various kind of responses are suitable to your application or not, and then you can move forward with designing those filters. So instead of writing a small program and then testing on that with frequency command, you can visualize directly here, and it will save a lot of time for you. So I hope you understand a lot about frequency filter design and analysis using Matlab Toolbox. So that's it for this video.